Okay, we're going to talk a little bit more about Gaussian elimination. So I'm going to assume that everybody here is familiar with matrix multiplication. That is to say, you can multiply two matrices A times B, and also the notion of the inverse of a matrix, that is A times A inverse is equal to the identity matrix. If you're not comfortable with these things, see section 1.4 in the book. So let's go ahead and look at Gaussian elimination again. So let's look at an example. Suppose you have this matrix and you apply Gaussian elimination to it. Well, you add minus 2 times the first row to the second, and it turns it into this matrix. Okay, that was easy. And I just want to revisit this and think of it in terms of matrix multiplication. This operation of adding the minus 2 times the first row to the second is exactly the same thing as multiplying on the left by this matrix. So let's just check that. If you multiply the matrix on the left like this, you get 1, 2, 0, and 1. So Gaussian elimination really just amounts to multiplying on the left, and since we're always adding a row, a multiple of a row, to a row below it, the matrix that we're multiplying is lower triangular. So to solve an equation like this, AX is equal to B, so I'm using matrix multiplication notation now to write a 2 by 2 system in this form. 1, 2, 2, 5 times XY is equal to, say, 5, 6. The idea is that you multiply both sides of this equation on the left by a matrix L, which is lower triangular. And you replace this equation with an equivalent one, LAX is equal to LB. And now you arrange that LA be upper triangular, and LB is just some new constant vector, so we've got an equation which is upper triangular. The system is upper triangular, and you can solve it by using back substitution. So that's the matrix version of the basic case of Gaussian elimination. So that brings us to something called the LU decomposition. This is a very important basic result in linear algebra. We're given a matrix A, and we try and write it in the form A is equal to LU, where L is a matrix of the form it has 1s on the diagonal, anything below the diagonal, and 0s above it, which is to say it's a lower triangular matrix, and it has 1s on the diagonal. And U is supposed to be of the form, well, it's allowed to have anything on the diagonal, but it's required to be upper triangular. And if you can do this, then what happens is, if you have an equation involving A, you can solve it as follows. So if we write A is equal to LU, then we can multiply both sides of this equation on the left by L inverse to get L inverse A is equal to U. And if L is lower triangular, L inverse is also lower triangular. And so we can use this to change the equation into an upper triangular one. We take AX is equal to B, and we convert it into L inverse AX is equal to L inverse B, which is to say UX is equal to B. And that's an upper triangular system which we can solve by back substitution. So there's a sort of an extra step here of moving the L from one side to the other by taking the inverse. So the question becomes, when can you write A is equal to LU, as discussed, where L and U are lower and upper triangular? Well, this is basically Gaussian elimination, and you can do it provided all of the pivots are non-zero. You just follow the Gaussian elimination algorithm, and this is exactly what you get. And what you wind up with is U becomes this upper triangular matrix, and one nice thing is that the diagonal entries turn out to be exactly the pivots. So let's go through an example of this. So suppose I started with this matrix. Well, the first step I do is I add a multiple of the first row to the second, and that amounts to multiplying by this matrix, and then I do it again, which is multiplying by this lower triangular matrix, and one last step, and it's become upper triangular. And these numbers here, 2, 2, and 3, are the pivots. And what I used here were these three lower triangular matrices. I'll label them L1, L2, and L3. And since the first thing that I did was use matrix L1, I multiply them in this order, sort of going backwards, and I've concluded that L3, L2, L1A is equal to U. Or if you want to bring those to the other side, you multiply the inverses in the opposite order to write A is equal to this thing. And this thing involving the L's is lower triangular. So we've got A is equal to LU, where L is, you just work out what this multiplication is, and it turns out to be this matrix. So let's look at how Gaussian elimination can fail. Well, we looked at an example like this last time. It fails right away here because we have a pivot which is equal to 0. And, well, there's an easy fix for this, which is we should switch the two rows. So if we do that, then we'll have 1 in the first pivot place and everything will be fine. And switching the two rows just amounts to multiplying on the left by this matrix. If you just work this out, multiplying on the left converts that matrix into this matrix. And then we go on our merry way and we can find the LU decomposition of this. So this matrix that we multiplied by on the left is an example of a permutation matrix. And what it does is it permutes the rows in an arbitrary way. And a permutation matrix is one where there's exactly a single 1 in each row and column. So if you do that, what you see is that you get what's called the permuted LU decomposition. Instead of A is equal to LU, you first multiply on the left by a permutation matrix to reorder the rows of A. And you'd like to do this so that all of the pivots are non-zero. And if that works, that's the permuted LU decomposition. And if A is non-singular, which is to say it's invertible, it has an inverse matrix, and that's exactly the same thing as saying that its determinant is not equal to 0. If that's the case, then this works. There is a permuted LU decomposition, which is to say you can find P, you can write PA is equal to LU. And again, where P is a permutation matrix and L is lower triangular with 1s on the diagonal, and U is upper triangular with anything on the diagonal, and these things will be non-zero since the matrix is invertible and those are the pivots. I'd like to go back to the LU decomposition now and give a small refinement of it. So suppose you've written a matrix A in its LU decomposition. So L is lower triangular with 1's on the diagonal and U is upper triangular, but it's not required to have 1's on the diagonal. So L and U are sort of treated differently here. Well, it's one small extra step removes that asymmetry. You write L as before, and now you just take the diagonal entries of U and put them in a diagonal matrix, and then you can write A as a product of 3 matrices where the last matrix is upper triangular with 1's on the diagonal. So this is lower triangular with 1's on the diagonal, and this matrix here on the right is upper triangular with 1's on the diagonal, and then what's in the middle is simply a diagonal matrix, and the diagonal entries are the pivots. So we call these L, D, and U, and so this is the LDU composition. A is equal to LDU, where L, D, and U are as above. And there's a crucial property of this decomposition, which is that L, D, and U are unique. There's only one way to write L, A in this form. L, D, and U are uniquely determined. Okay, there's one last thing to talk about in this topic of Gaussian elimination, which is to look at the case of symmetric matrices. So here's an example of a symmetric matrix. It's symmetric when you reflect it about the diagonal. 2, 2, 4, 4, and 3, 3 all match up. And these are an important family of matrices. So we define the transpose of a matrix to be what you get when you flip it about the diagonal. This is an operation on matrices. A, B, C, D transpose is A, B, C, D flipped around the diagonal like this. And so it's easy to see that a matrix is symmetric exactly when it's equal to its own transpose. That's a convenient formulation of the notion of a symmetric matrix. Now this operation of transpose, there's a natural question which comes up about it. If you take the transpose of A, B, is that the transpose of A times the transpose of B? Well, the fact that I put a question mark there means that it's probably not true, and in fact it's not. But what's true is that when you take the transpose, you get B transpose, A transpose, and you just have to reverse the order of the A and the B. Okay, so that's a basic fact about the transpose operation. So now let's look at the LDU decomposition for symmetric matrices. So suppose I have a symmetric matrix, and I write it. Suppose I have its LDU decomposition. Well, if you take its transpose, you get the transpose of LDU, and by what I just said, you reverse the order on the right-hand side. You get U transpose, D transpose, L transpose. And D transpose is itself, because D is diagonal, so you get this. And what you conclude is that LDU, which is A, is also equal to U transpose D L transpose. But now notice that both L and U transpose are lower triangular, because transpose exchanges lower and upper triangular. And similarly with U and L transpose. And so by uniqueness, it must be that U transpose is equal to L and U is equal to L transpose. So the conclusion is that if you have the LDU decomposition for a symmetric matrix, in fact, the way you've written it is as LDL transpose. So that's the LDU decomposition for a symmetric matrix.